Testing series can be difficult at times, especially because there are many tests available, and sometimes we are in doubt which test to be used. So in this one, we can discuss how to know which test to use. Especially that depends on what kind of series we have. So what we're gonna do is we can look at the term, the nth term, and figure out what is the right test. So let's learn some strategies to do it. And before we do that, and we know that there are two type of questions. So there are two type of questions, two types of questions. So the first one is it can just ask whether the test is converging or diverging. So the first type of question is test whether uh, the series converge or diverge, converge or diverge. So that is the first type of question. So the second type of question, if the series converge, then they can ask you whether what is the sum of the series. So find the sum of the series. So find the sum of the series. But so this question is only valid when the series converge. Okay, so only when series converges, because if the series diverge, we can talk about sum. There's no, because it's gonna fluctuate. Okay, so but in this time, if they ask you what is the sum, and there are only two ways to do it in a, like a general setting, but there are some special techniques for special type of series, but we talk about in calculus 2 only two methods. So the first one is so if you ask to find the sum of the series, there are only two types. The first one is the series has to be geometric. So if the series is geometric, so geometric series, then we can find the sum. We know that if the series is geometric and if the series is converging, then we know that we can write this one as sigma. Let's say n going from 1 to infinity, a. We know that the nth term you can write as a n a r n minus 1, which is equals to first term. How to get the first term? Plug in the first value of n. So the first value is n is 1. If you plug n equal 1, you're gonna see that it is a r0. r0 means 1, so that means a. So the first term divided by 1 minus r. That's why it converges. This happens when the absolute value of r is less than 1. So in this case, the series is going to converge. So series is going to converge in this case, and it's going to converge to a over 1 minus r. So that is the sum of the series going to converge to this value. And then we also know that it's going to diverge. So I'm going to write it. So if r greater than 1, so you can see if r greater than or equal to 1, if the absolute value of r greater than or equal to 1, the series is going to diverge. So the series is going to diverge. In that case, we cannot talk about sum, because there's no finite sum in that case. So it's the only case is when absolute value of r less than 1. So that is one type. This other type is if the series is telescoping. So if the series is telescoping series, so it's a telescoping series, then we can also find the sum. So what's happening that the telescoping series, let's say you have a series sigma an, we just write an. Index can be any value that you want to write, but just write sigma an. So telescoping means the nth term an can be written as a sum of not the sum, the difference of two consecutive terms. So the best way to write that in mathematics, if you have a function, is fn minus n plus 1. So you can see these are two consecutive terms. So if you can write the nth term as a difference of two consecutive terms, what you get is what we call a telescoping series. So you can write this one as, so this is what you get is simply a difference of, so you can see what is this. So this is a difference of two consecutive terms, two consecutive terms, consecutive terms. Okay, so if you can write the n term as a difference of two consecutive terms, what we get is called a telescoping series. In this case, we can also find the sum. So let's see how we can do it. So this is what's going to happen in this case. So what we notice is that, so we have a sequence, and where n term can be written as a difference of two functions. So in this case, what we can do, let's look at the partial sum. So that means you can sum it to, you can add the first n terms. So that means it is Sn, we write Sn, the sum of the first n terms. That means n going from 1 to n. It's a kind of bad notation. So sometimes, because you cannot have n here and n there, so maybe it's a good idea to write, use some other notation just to make it very clear. So let's say we can use k going from 1 to n. So that means k starting value is 1, so and then a to the k, so that's the best way to write it. So that means what? Starting value 1, so that means a1 plus a2 plus a3, like that. So and go up to the n, an. Now what we can do, you can see that you can replace each of the terms by that fn. So that means the first term simply going to be f1 minus f2, because if you plug in 1, that's what you get. Okay, and then that's the first term. So what's the second term? The second term is, if you plug in n equal to, it is f2 minus f3, and you can see, and the next term is f3 minus f4. So that's what's going to happen. And if you look at the n term, you can see it is fn minus fn plus 1. So this is what happened. But you can see, if you look at this sum, you can see this is f2, and f2 get cancelled because one is plus and one is minus. And similarly, you can see that f3 and f3 get cancelled because one is plus, one is minus. So same thing gonna happen like that. So that in f3, f4 cancel the next one, and then this one also get cancelled out. So that means you simply have two terms. What are the two terms? You can have the first term and the last term. So this is what you get. Now the question is whether this can converge or diverge. So you can see that if the limit of the last term, if the limit of this term is 0, that means something interesting happened. So that's the only case is interesting. So we can see if the limit when it goes to infinity, if n plus 1 equals 0, what's going to happen? This term disappear. So in that case, you can write this one. So that means S infinity, that means sum of all the terms. So this is simply, we can write as n goes to n going from, so let's say like this, let's write this as a limit. So that means it is simply limit n goes to infinity. So you can look at the sum. So k going from 1 to n, ak. So in that case, but we know that the partial sum, we show that the partial sum is simply, so it's a limit, it is simply f1 minus fn plus 1, but we know that here this term goes to 0 because we see the limit is 0, so that means we simply get f1. So that means the sum of the telescoping series. So the telescoping means this idea. So you can see, so what's going to happen here, so this part. So what's happening here is what we call the telescoping. So this is cancelling out. So I can write it like this. So if you look at this one, so this cancelling out is called the telescoping. They cancel out. Okay, so that's the idea. So now you can see that, so they cancel out and get the first one, the last one. So that means you can sum up to F1. So this is the idea of how to use the telescope in series, and you can try these problems as practice problems. So I'm going to give you 3 problems just to try see whether it's going to work. So the first one is sigma n going from 1 to infinity 1 over n minus 1 over n plus 1. So you can see this is a difference of 2 terms. So it's already there. What you need to do is look at the partial sum and cancel out the terms and then simplify, and then you can see that it's nicely uh, cancel out and get the answer. And then the next one is, how about this one, sigma n going from 1 to infinity 3 over, so let's say 4n squared minus 1, something like that. So only problem is here you don't see the fact the term. So what you want to do is think about the factors of the bottom and then write as a difference. So how to do that? You have to use partial fractions. Use partial fractions to write this as a difference. Okay, you can look at the original video about this. There's a video, like complete video for that, and that explains this exact same problem. What you normally do is you need to think of the factors. You can see you can factor this one as how to factor this one. You can see you can factor this one as 2n minus 1 and then 2n plus 1. So those are 2 factors, and you can see that those are 2 consecutive terms. So what you want to write, you use the partial fraction method to find the const the terms and then write as a difference. Okay, and then why don't you try this? So sometimes there are some problems, it doesn't look like this type, but for example this problem, n can going from 1 to infinity ln n over n plus 1. And you can see that you can use one of the log properties, because we know that in log, when you have a quotient, that becomes a difference. So if you write it like that, and you can see that this is a telescope in series, unfortunately diverging. Okay, and also you can try this problem as well. So you can see n going from 1 to infinity, a little complicated one, 5 over 4n squared plus 8n plus 3. This problem is very similar to the second one, but you need to think of factors and write as you write using partial fractions. So this is the idea, and see whether you can do it. And now let's turn to the main problem. So what is the main problem? So test whether the series converge or diverge. Okay, so that's the main question. So, and we know that there are a lot of tests, and the question is which one to use. So if you just try to use a random one or like all of them one by one, that is really not the right way to do it, because there are like some easy tricks that you can remember, and it's gonna make it very easy. So normally the very first one we try is, I'm gonna call number 1, is the test for divergence. That is something that we test at the beginning. Okay, so test for divergence. Test for divergence. That's the kind of first test to use. So what we're going to do in the test for divergence, so let's say divergence of the series sigma n. So we have series like that, and we're going to, so what we're going to do, we can look at the limit of the nth term. So we can check, so if the limit, when n goes to infinity, an, so we can look at the limit of the nth term. If it is not equal to 0, if it is not equal to 0, that means it's not equal to 0 can be in 2 ways. One is it get a number other than 0, or it can go to positive infinity, or it can go to negative infinity, or it can even fluctuate, like does not exist situation. So it's a plus or minus infinity, does not exist, or something other than 0. In any of those ways, it can be not equal to 0. If any of that happens, then what we know is, then we know the series diverge. So series diverges. Unfortunately, this only works when the series diverge. So if the limit is 0, it doesn't say anything. It doesn't say anything. Uh, so that we need to understand. So the note is, so let's write it. So the note, if the limit is 0, if the limit n goes to infinity, n equals 0, it does not imply convergence. Okay, does not imply convergence. So please remember that. So if it is 0, it doesn't mean anything. But if it's not equal to 0, it means that the series has to diverge. So these are the kind of problems that you can try. Um, so I'm going to give these as practice problems or exercise. So you can try them. So under this one. So in going from 1 to infinity, 3n minus 4 divided by 4n plus 3. Okay. So try that, and you can see that if you look at the limit, it's just 3/4. Because these kind of ones, it's very easy to find the limit if the because this is a very special situation, because we see that the limit when n goes to infinity. So finding a limit when n goes to infinity is easy compared to other limits. So in this case, if the numerator and the denominator have the exact same degree, in this case 1 1, the limit has to be simply 3/4. So that's the limit. It's going to be 3/4. That's a kind of shortcut for polynomials with what we call rational functions with the same degree in the denominator and the numerator. If they are the same degree in the numerator and the denominator, the limit is simply the ratio of the coefficients of the largest terms. Okay, so use that. So we don't need L'Hopital's rule or anything for these kind of problems, and don't abuse the L'Hopital's rule for this problem. It's just very easy. Okay, good. And you can try a few more. So this is another problem that you can try. So sigma n going from, it's not always 1. How about 2? So it doesn't really matter for convergence. So it only matters what is the sum. It changes the sum, but it does not change the convergence even if you start with some numbers other than 1. So 3n squared minus n plus 1 divided by, let's say, 5n squared plus 3n plus 2, something like that. And you can see that here numerator derivative has the exact same degree, so that means we know the limit is 3/5, but there's a minus 1 to the n. That means it's going to fluctuate between negative 3/5 and positive 3/5. That means the limit does not exist in this case. That means the series has to diverge. And also a few other examples. So these are all problems that's going to go under this category. How about this one? So you can see n going from 0 to infinity, n minus 3 over n to the nth power. So this is also a situation like that. So in this problem, you might use one result from calculus. Maybe you remember that the limit when n goes to infinity, 1 plus x over n to the nth power. So this is simply equal to e to the x. So you might need to use that here. Okay, so that's the hint. And how about a few more? So for example, this one, sigma n going from 0 to infinity, n sine 1 over n. So think about this one. So what you can do is you can bring this n down. You can divide the top number term by n. So then you're going to get sine 1 over n divided by 1 over n. This is a really interesting example because when n goes to infinity, 1 over n goes to 0. So this is like sine x over x when x goes to 0 situation. We know that when x goes to 0, sine x over x is 1. So that means in this case, n sine 1 over n goes to 1. So which is not equal to 0. That means it has to diverge. Get. So I'm not solving any problems here. You need to try the purpose of this video is to figure out what test to use, not how to use it. Okay. And then this one also. So this is n over n plus 1. This is a little tricky problem to the nth power. This is very similar to the third problem, but think about how to do this one. Maybe you need to bring it down first. And then as the last one, why don't try this? N going from 1 to infinity, negative 1 to the nth power cosine 1 over n squared. Yeah, think about this. Okay, so these are the kind of problems that we can try under the test for divergence. So always that is the first thing we try. We try whether the limit is 0 or not. Okay, so let's go to the next one. So the next important one is what we're trying to do is we're going to check whether the given series is a P series. So the next one, which is number 2, a P series. P series. So what's a P series? P series means you have series. I'm gonna just say 1. You don't need 1 always, which has the format 1 over n to the p power. That's what we call P series. So if you have P series, and we know that there are two things can happen. So what are those two things? We know that can converge. The series can converge if p greater than 1. It's going to diverge if p less than or equal to 1. Okay, converge if p greater than 1, diverge if p less than or equal to 1. So that means if we draw a line, this is what's going to happen. So this is the number line. So let's put the numbers here. So it's 0, and then the critical number is 1. So what it says that if it is bigger than 1, it's going to converge. If on the other side, it's going to diverge. So if we have negative infinity all the way up to 1, it's going to diverge. And from 1 to positive infinity, it's going to converge. Okay, so converge and diverge. So so 1 is the point, but it has to be bigger than 1. Then it's going to converge. Okay, so that's the one. And then what are the special cases? So there's a very special case. So let's start the special case, what we call the harmonic series. Special case is the harmonic series. So what we normally call the harmonic series, that is when p is equals to 1. So that means sigma n going from 1 to infinity, 1 over n to the 1, so it's simply 1 over n. So that means you write the terms, you get 1, and then when you apply n equal 2, 1/2, n equal 3, 1/3, like that. That's the harmonic series. And according to the P series test, because here n equal 1, so this one diverges. Okay, so this one diverges. So that means that we can use series test if the series is close to or similar to a P series. So that means if the series if the series is similar or close to, okay, similar to a, if the series is similar to a p series. If the series is similar to a p series, we're going to use the p series test. So for example, if you have, so these are the problems that you can try. So let's say you have problem like this. So n going from 1 to infinity, simply 1 over n squared. So this is very clear that it's a p series, p equal 2. So it has to converge. And how about the next one? So let's say sigma n going from, it doesn't matter what the starting value, let's say 5 to infinity. 4 divided by n to the 2/3. 4 is just a number, so you can pull it out. So that means you're gonna get 1 over n to the 2/3. 2/3 is, that's the p-value, 2/3, which is less than 1. So that means series has to diverge. First one converge because p greater than 1. Second one diverge. And then let's try this one. So the next one, n going from 1 to infinity, 7 over n to the pi divided by e. So for this one, you need to know what are those values. So I'm going to give you those values. So pi is roughly equal to 3.1415 like that. And e is approximately equal to 2.7182 like that. Okay, so remember those rough values because that can help you sometimes, but that won't be given. So think about what is the p-value in this case. A 7 is just a number, you can pull it out. And also there are some series which are not really power series, which are not really p series, but it can be very close. So for example, any starting with -1, 3 over n plus 2. It's just a shifting because otherwise and 1.3 something like that. So you can see that it is just a shifting. N plus 2, what the plus 2 does, it just shift, so it doesn't change the convergence. So you can simply treat this one exactly like a p series. You only need to look at the p value. In this case p is 1.3, so this has to converge because it's a larger than 1. So it is just a shifting of the values, but otherwise there's nothing, no big difference this one. So these are the kind of things that you can, so if you see a series like that, you don't need to waste too much time. Just go with the p series, look at the p value, and then you can see if this converge or diverge. Okay, so that's the second type. So let's look at the third type, third important type. So what we're going to do, we're going to start with the test for divergence first. If that doesn't look like, then we look at whether it's a p series. Okay, but if you see that's a p series, you don't want to go for the test for divergence, just go for the p series. Okay, good. So let's look at the next one. Next one is the geometric series. This is number 3. Geometric series. Geometric series. So if you see, so what is geometric series? Geometric series means you can start with a number and then you're going to multiply by a constant. So we normally use the r for that constant. So it's ar squared, like that. Every time you multiply by r, that's what we call a geometric series. So if you look at the general term, it looks like ar n minus 1. Why minus 1? You can see that the first one doesn't have a term. So 1 actually comes for the second term. That's why I say n minus 1. Now what we know that this series you can write in this form. So you can say it is a r n minus 1, and you can see n gonna start with 1, so 1 to infinity. So that is how you can write the series. So we can write it like that. That's a whole series, but we don't know whether it's a number or not. So, but we know that this one converges to a number. You get a number which is the first term, but at the first term divided by 1 minus r if the absolute value of r less than 1. Absolute value of r less than 1. Okay, it's absolute value. And then it's going to diverge. So yeah, and then what's going to happen? The other one is it's going to diverge. So diverge diverges if the absolute value of r greater than or equal to 1. So you can see there's a like a difference between the p series and the geometric series. So let's try to kind of draw the region where it's going to converge, the values of r where it's going to converge. So we can see, so we draw it on a line, that's the number 0, and you can see it's going to converge between -1 and +1. So this is a -1 and +1. That's the only place where it's going to converge. That's where it's going to converge between +1 and -1. And outside it's going to diverge. So it's going to converge here and diverge outside. So try to remember this along with the region for the P series, because the P series is going to converge for any value which is larger than 1. That's for the P series. But for geometric series, it is in between 1 and -1. So if you have any value between -1 and 1, it's going to converge, excluding, okay, not including, excluding. And outside, it's going to diverge. Good. And also sometimes we can also write the P series, geometric series as a to the Rn. But if you write the P series as sigma like this, so sometimes we write this as ARn. But if you write ARn, in this case n star is 0 to infinity, okay? Because otherwise you can't get the first term. So you have to be careful how we write it, whether you write ARn or a to the Rn minus 1. Okay, yeah, so in this case, so where it's going to diverge from 1 to infinity or -infinity to -1. Okay, so in this true region it's going to diverge. Good. So now the question is, so we can say, so if we can say if the series of the form, if the series of the form sigma ARn minus 1 or sigma ARn or any other value, because you have any other form, only thing is what is the first index value, whether n equals 0, n equal 1 or any other n value. So if this is the case, we use the geometric series. Okay, so use geometric series test. Geometric series test. Good. What's the geometric series test? If r less than or equal 1 converge, so it is simply absolute r less than 1 converges if the absolute value of r greater than or equal 1 is going to diverge. Okay, so if you need to find only whether it's converge or diverge, and that's it, you just look at the absolute value of r. That's going to tell you whether it's converge or diverge. But if you need the sum, then you need to continue and use the a over 1 minus r to find the sum. Good. So these are the kind of problems that you can try under this technique. So you can try these. So exercises are going to be problems like this. Sigma n going from 1 to infinity for 1/5 to the nth power. Here it is very clear. R is simply 1/5, so this has to, and then it is less than 1, so it has to converge. And a problem like this, sigma n going from 1 to infinity. So how about not 1? Let's say 4. It's only change the value but not the convergence. So let's say it's -2 divided by 3 to the n. Okay, like that. So you need to figure out what is the r value in this case. -2 only contribute to the initial term. So in this case, r is simply 1/3. So which is less than 1. So that means it has to converge. And if you know the sum, you can use the formula. Okay, so another problem you can try is in going from 3 to infinity, -1 to the n, 7 over 4n. 4n. Okay. Uh, so let's try a few more problems. So how about this one? So let's say sigma k going from 1 to infinity. So you can say 3k plus 4k over 5k, like that. So what you want to do, you want to split this into two geometric series. Okay. And then more. So you can just try them. So how about if you flip it, like 5k, let's say start with 5k over 3k plus 4k. Think about how to do this. You may have to use the test for divergence because you need to check the limit. What happened to the limit? Okay. So the next one, n going from 2 to infinity to n minus -1 to the n, 3n, and then 6n. You may have to split and find the r value. So there are two series actually here. So you can split this into two series. And another one like that, k going from 1 to infinity, 1 over k to the cube minus 1 over 3 to the k. Again, split this as two series. Maybe one last one. We can try this one. We can say sigma n equal 2 to infinity. Let's say -1 to the n, -1 n minus 1. Yeah, I'm going to write it. Yeah, -1 n minus 1. And then, yeah, let's start it here because I need more space for that. So how about this? Sigma n going from 2 to infinity, -1 n minus 1, 2 to the n minus 1, 3 to the n plus 1 over 12n, something like that. So it's going to be very complicated, but you can see that still what you're going to do is you're going to combine all the terms with the power of n and take the rest out. So we have done similar problems in the general video, but here this is the kind of collection that we have everything. So yeah, so you can see that here you can find the r value. That's not that bad. So you can see r has to be in this case 2 to the n, 3 to the n over 12n. If you combine all the n terms, it is 2 times 3 over 12. That means 1/2. So r is 1/2 actually, because, and then also there's a -1 to the n, that means r equal -1/2. So that's what you get in this problem. Okay, I'm going to write only for this problem, r has to be -1/2. See whether you get the same answer. Good. To find a, what you want to do is plug in n equal 2 wherever you see n. That's going to give you the a value. Okay, so this is r is less than 1/2. R is -1/2, absolute value is 1/2, which is less than 1, so it has to converge. So it's a convergence series. Okay, so that's about that. And also there's another type of problem. So that's that. And then second type is sometimes what happen, they're gonna give you the series as like a sum like this. So let's say 3 minus 1/2 plus 112 minus 1 over 72, like that. Sometimes they give a series like that. So if you get a series like that, you want to check whether this is a geometric series first. So how to do that? you can divide. You're going to divide the terms, consecutive terms. That's in this case negative 1/2 divided by 3. If you do that, you get negative 1/6. And do the same thing. You just divide. So if you divide the next two, so I'm going to divide these two because I don't have much space here. So let's see. Let's divide. And then you're going to get negative 1/72 divided by negative 1/12. So how to do this? A negative, you can divide the denominators, and you can see that so this is negative 172 times, it's a division, that means you make it upside down, so it's a 12/1. That means you're going to get negative 1/6 again. So that means they are the same. You can see these numbers are the same, and that's the R value. So in this case R is equal to negative 1/6. That means the absolute value of R is 1/6, which is less than 1. So that means converge. Okay, converge. So it's going to converge to the first term divided by 1 minus R. First term is 3. 1 minus R means negative 1/6. Don't forget the negative sign. And so this is 3/1 plus 1/6. If you multiply by 6, top and bottom, you get 18/6 plus 1. So that means it is 18/7. So that's where it's going to converge to 18/7. But this is how you do it if you get a series like that. So it's not that bad. You can divide, find R, and then look at the absolute value of R. That's going to tell you what's going to happen. Good, so that's about that, and you can try the rest of the problems. And if you get stuck, look at the general video. There's a video called all-in-one series test, and that have a lot of problems that you can learn, if all the missing things. Okay, so let's go for that. The next one we're gonna do is we're gonna look at the comparison tests. So let's talk about that. So this is number 4. So we're gonna test for comparison. Go for comparison test. Okay, comparison tests. Comparison tests. So what we're gonna do now, the question is when to use it. So what we're gonna do is so let's talk about that. So use when, okay, used when the series, the given series, use when the given series is similar to a p series, or geometric series. That's the case. Okay, that's when we're going to use it. So you're going to see something which is very close to a p series. It's not exactly p series, but close to it. So that means we can do some simplification. That's the whole point. And then what we gonna do is compare with let's say compare with another series, That's the whole point. That's why we call comparison. You compare with another series of which the convergence is known. Convergence is known. Okay, convergence is known. So we're gonna test with something of which the convergence is known. Now the question is how to find the second series. To find the second series, we can do some kind of simplification. We consider only the largest terms of the numerator and denominator if the terms are like that. So because you have to compare with another series, what we normally call second series. So the comparison series. So let's say second series. Okay, so second series is obtained by simplifying I'm going to call it simplifying. Okay, so by simplifying the first series, simplifying the first series, simplifying the first series. So there are two tests, two major tests. So what we can do, there are two tests. So what are the two tests? So this for positive terms. It's very important for positive terms. For positive terms. So there are two tests. The first one is what we call the direct comparison test. So let's look at that. I'm going to write it just for clarity. That's not the point of writing, working here. I don't want to write it here, but it's like as just all in one. So let's put it there in short. Okay. So the first one is what we call the direct comparison test. Direct comparison test. So what we normally call DCT, direct comparison test, or DCT. So what is that? So we're going to suppose, that's the assumption. Suppose these terms are positive and an less than or equal bn. This even can be 0. Bn for some n, like what we normally call eventually. Okay, after some n, this is the case. So at the beginning we don't care. So we see what's going to happen after some n. This works. Okay. Then what it says, there are two things. If the larger one converges, if the larger one, that means Bn converges, if the larger one converges, then the smaller one has to converge. If the smaller one diverges, then the larger one diverges. See the direction. So it's a kind of squeezing here. So you can see if the larger one converge, if that's a larger one, if that has a finite value, then the automatically smaller one should have a finite value. And if the smaller one diverge, then that's kind of push the other one. So that means the larger one has to diverge. So that's how it works. So this is what we call the direct comparison test. So what is more important is what we call the limit comparison test. Anywhere the direct comparison test works, limit comparison test always works. But limit comparison test has some extra work to do. So that's why it's not always the best one, but it works every time the direct comparison test works. So let's try the limit comparison test now. So the limit comparison test, limit comparison test, or we call LCT. So in this case, so we have two series, sigma an compare with sigma bn. Okay, and we also assume that those terms are not equal to 0, especially the one you can divide. Okay, so now what we can do, if the limit when it goes to infinity an over bn, if the limit, let's say you get a number other than 0. If you get a 0 case, that's a special situation, we have to consider that separately. If you get a number other than 0, then what it says that the two series behave exactly the same way. So that means we're gonna say two series either converge or diverge. What does that mean? Two behave exact same way. So that means if one converge, the other one converge. If one diverge, the other one diverge. So what does that mean? What does that mean that you get a limit a constant? You get a limit a constant means the terms of one series are just a constant multiple of the other one for large n, or very close to. So it's a limit. So very close to a constant multiple of the other one. So just a constant multiple. That means you can pull the multiple out. So what's going to happen? So that's why the two series behave the exact same way, because they're controlled by the other one. Okay, that's the whole point. Okay, so this very powerful test. And then yeah. So and then how we normally remember this one behaves the same way. Okay, right? So behaves the same. Remember like that. That's what the limit comparison test means. Behaves the exact same way. One diverge, the other one diverge. One converge, the other one converge. Okay, good. And then if the limit is 0, you have to consider different cases. If the limit is 0, then you can see that bottom one is going much slower. Okay, that's what it means. So that means if the the series from the bottom one converge, the top one has to converge. And if you get a number which is like if you get infinity, that means if the bottom one diverge, the top one has to diverge. So it's like depending on 0. So 0 means the top one go much, the terms compared to the terms of the bottom one, the terms of the top one is much smaller. That's what the limit 0 means. If you get infinity, that means the compare the terms of the bottom one, terms of the top one is larger. Okay, so that's the kind of idea. Okay, so and then um, what if you have some terms? So this is a part of the comparison test also. So let's say there are some terms which are have negative terms. So if there are some negative terms, not all, I mean some negative terms, if all negative terms are negative, then you can pull the negatives out. Then you can simply consider this as a positive series. But sometimes some terms are positive, some terms are negative. In that case, what we can do, we consider we look at the absolute values. Okay, so if let's say sigma an has negative terms, or say some negative terms, okay, negative terms, what we can do, try the absolute convergence test. Try absolute convergence test. Okay, try absolute convergence test, what we call ACT, absolute convergence test, or insert ACT. So what is that? The absolute convergence test, if the series absolutely converge, the original series converge. So let's write it. So absolute convergence test. Absolute convergence test. So so this says that if sigma an, the absolute value of the series converges, then the original series has to converge. The reason is the absolute series are only positive terms. So there are no plus or minus terms. That means even if with plus terms, if it can converge, that means it's going to get a finite value. It is very clear that the other one has to have a finite value as well. So that's true. Okay. So those are the the few convergence tests, and then I'm going to give you some problems that you can try. So these are the kind of problems that you can try under these techniques. And also there's a very important uh, fact that you need to remember. So I'm going to write this as a note. So remember these relations. These are very useful. So one relation is this one. So you can remember that ln n is smaller than n, and which is smaller than let's say n squared, which is smaller than 2 to the n, which is smaller than n factorial, and which is smaller than n to the n. So this relation is going to help you a lot, especially when you do comparison test. So ln n is the smallest, and then n squared, n 2 to the n factorial, and n to the n. This also works with any other numbers, like even if you replace this 2 by 3, it works. Okay, so it works for any other numbers as well. I just picked 2 as an example. And the other one that you can remember is this one. So n less than e to the n, and then less than factorial n, and then less than n to the n. So this is for large n. So this is for large n. So this is also useful. So those two results are very useful, and then we can use this in many cases, especially when you do some kind of comparison. So I put this in a box. Good. So these are the problems that we can try under this technique. So you can try these problems under these comparison tests. So exercise, you can try this. Sigma n going from 1 to infinity, 1 over n squared plus 1. You can see, you can compare this one with 1 over n squared. And then try this. N going from 2 to infinity, 3 over n minus 1. This is just a direct comparison problems. And then sigma n going from 1 to infinity, 1 over n factorial, and then sigma n going from 1 to infinity, ln n over n, and then sigma n going from, okay, we're going to do n over ln n, but you have to be careful. You can't say n equal 1 now, because n equal 1 is 0. So I'm start with another value, n going from 2 to infinity. You can put 1 here. Good. And then we can try this. Sigma n going from 1 to infinity, n over n factorial, and then n going from 1 to infinity, n factorial over 3n. You can see that from the result that we just had, n divided by n factorial is bigger than 1. So you can see that it's always bigger than 1. So this term is bigger than 1. So that means you can compare the series with sigma 1. Sigma just 1. Because since you are adding 1, 1, 1, that diverge, so this has to diverge. Same thing. You can see this one also bigger than 1. Okay. When in for large n, okay, not for all n, but for large n, because we only worry about what happens in large n. So you have to say for large n. Okay, for large n, this is greater than 1. Good. Okay. So you can see it's very simple. And then, so we have this one, sigma n going from 2 to infinity, we can say 3n over ln n, and then sigma n going from 1 to infinity, 5 divided by 2 plus 6 to the n. So you can use comparison test along with the geometric series here. And then so these are like some of the things that you can try. Can write one more here, a space 1 to infinity 1 over 5n plus n. Okay, so you have to use the comparison first, the direct comparison, and then you have to use a geometric series. So direct comparison and geometry. Okay, you have to use some geometric series here. You can see they have some pattern of geometric series. So it is direct comparison test plus geometric. Good. And then like problems like that. So these are very typical examples of a limit comparison test, n over n3 plus 1. And this one also you can do from the direct comparison. But if you have n3, if you have n over n3 minus 1, now you can have n equal 1 because it can make denominator 0, but I'm going to say n equal 2. Now you cannot use the direct comparison, but you can still use the limit comparison for this. So I want to say this is a direct comparison test problem, this is a limit comparison test problem. See the difference, just one number plus in the denominator, plus 1 minus 1 change the test completely. And then this one, let's say k going from 1 to infinity 1 over k, and then k squared plus 1 square root, something like that. This is simply a limit comparison problem. Good. And then we can have a few more. So like you can see there are a lot of this category. So we can have n going from 1 to infinity. So this is a very typical example of the limit comparison test. So some algebraic expressions, you always try the limit comparison, it's much simpler. So this is definitely a limit comparison problem. And then when you have like complicated expressions like this is always a limit comparison problem. So let's say n squared minus 1 to the cube root divided by n fifth minus 2 sine n plus 7 square root. Okay, when you have expressions like that, always a limit comparison problem. It's very easy to use a limit comparison problem. Okay, and then how about these ones? So sigma n going from 1 to infinity 1 over n squared cosine n. Okay, so think about why we have, because we see that cosine n, we don't know whether it's always positive, it can fluctuate between positive and negative. So a good idea would be the absolute convergence test. So absolute convergence test for this one, because cosine can change the sign. And then now we know the idea, so we can say we can try these. Negative 1 to the n minus 1, this is sine n squared divided by n, something like that. So good. So actually if we have something like this with a n, we can't say anything, but if you have like a cube, even a square, yeah, with a square you can try, and you can see this is a absolute convergence problem. And then these ones, these are last few problems that I'm going to put it here under this category. So you can see sigma n going from 1 to infinity, -1 to the n over n cube square root, and then sigma n going from 1 to infinity, -1 n over absolute on the factorial n, and then sigma n going from 1 to infinity sine 2n over 1 plus 2n. Just try as much as you can depending on how much time you have. You don't want to try all of them, but you can see. So what are you going to put all of them here? You can see these are all under those three types: the direct comparison test, limit comparison test, or the absolute convergence test. Especially the last five works on the absolute convergence test. Good. Yeah. So there's a 2 here. Good. So you can try those. Try as much as you can, but you can see what I want to show you the category. So this go under absolute convergence test category. I'm sorry. This go under this all of them go under direct comparison test, limit comparison test, or absolute convergence tests. Okay. So let's go to the next type. What we're going to do, the alternate series test. So you can see there are a lot of problems that you can do from the just basic comparison test, direct, limit, or absolute convergence. Okay, so let's go to the next type, which is the alternate series test. Number 5, alternate series test. Alternating series tests, what we normally call AST. That's the very common name to say it, AST. Alternate series test. So, we're going to use this for series of the form. For series of the form some, so -1 to some power and bn. So it has to be of this form, okay, where bn is positive or 0. Also, you can see that the same series you can write in several different ways. So you can write this one as sigma -1 n minus 1 bn, or you can also say n, so -1 n plus 1 bn. So there are a lot of other ways, but they are all the same thing. So the alternate series test, I have two things. So one is the limit, n goes to infinity, bn equals 0. We don't use an. The reason is we normally call an is the nth term, so we want to stay away from that. That's why we did not use an. We go with bn. And then the second condition is, there are two conditions. The second condition is the limit of bn. The limit of bn has to be decreasing. So it is bn plus 1. The next term is smaller than the previous one. That means they are decreasing eventually. Okay, we call eventually. We don't need that for all, but after some n, it should happen. Okay, so this is what we call, or this is like simply means that bn is decreasing. Okay, so bn is decreasing. That's what it means. Then what it says, then the series converge. Then the sigma -1 to n bn, whatever the original series, converges. So this is a very powerful result because there are a lot of things. We use this a lot, especially when you do Taylor series, Taylor expansions, Taylor series, power series, macromolar series. All of them we use this a lot. Okay, so and there's a small note. So what the note says that if the limit if the limit n goes to infinity bn not equal to 0, if you get something like that, then we can see the series diverge. Okay, this is part of the divergence test. Then the series -1 n bn diverges. Okay, diverges. Okay, so these are the kind of problems that we can try under this technique. So try these. So let's say sigma n going from 1 to infinity, -1 to the n over absolute, no, square root n. Okay? Of course, because you can see this is of the right form, then you can see this gonna under this this ordinary series test candidate. How about this one? N going from, let's say, 2 to infinity, -1 n over ln n, and you can see it satisfy all the nice conditions, and you can start with n equal 1 here because you have ln n. And the next one is n going from 1 to infinity, -1 n squared plus 1 over n to the 4th plus 3, something like that. And then this one, sigma n going from 1 to infinity, -1 n over n squared plus 1. So you can, yeah, so these are all nice candidates for the alternating series test because they alternate, and then you can try these. And then I'm gonna give you one last problem. So why don't you try this one also? N going from 2 to infinity, actually 1 to infinity. Yeah, as you can see, yeah, any number, it doesn't really matter. -1 n over, let's say 1 minus 2 over n to the nth power. Okay, something like that. That's a very special problem. Okay, so these are some candidates for the alternating series tests. Now we're gonna go to the ratio test. That's one of the another powerful test. So let's look at the so again we use the alternate series test when you see problem like terms with the -1 to the nth term times some bn. Okay, and we try the alternate series test. Okay, let's go to the next. So the number 6, this is the ratio test. Ratio test. So ratio test is typically used for series with terms like factorial or some constant to a n. It doesn't matter about the constant. So those are the two typical candidates. If you see factorial or if you see like a constant terms like that, we can use a ratio test. So let's look at the ratio test. Ratio test. So what the ratio test is, so let's say you have sigma an, and we assume that those terms are not equal to 0 because you can take the ratio. So what we can do, we can say a ratio, I'm going to call the rho. So what is that? It's a limit when n goes to infinity, an plus 1 divided by an. So what we do, and take the absolute value. We take the absolute value and divide two consecutive terms, the second later one in the top. And then what's going to happen is, once you find this limit, so three things can happen. One is, it can be less than 1. You get a value which is less than 1. This is positive. So less than 1 means it can be 0 or anything less than 1. If this is the case, what's going to happen? This actually converge absolutely. Absolute convergence implies converge. So it simply converge. Okay. So converges, actually what exactly happens is absolutely converge. Okay, so absolutely converge. If this is greater than 1, it's gonna diverge. And then sometimes what happen, you get a limit which is exactly equal to 1. So if you get something which is equal to 1, then what's going to happen is this test is inconclusive. So you cannot say anything. Inconclusive. Inconclusive. So in this case, we have to use other test. Use other tests. Okay. Good. So that's the kind of idea. So I'm going to give you some typical examples that you can try. So look for the factorial or constant terms. So those are typical problems that we can try under this technique. So these are a few of those examples. So in going from 1 to infinity, let's say 3n over n factorial. Good. So you can use the direct comparison test for this problem. But if you have upside down factorial n over 3n, then you don't want to use the ratio test, is too long. You can just use the direct comparison test. Okay, but here you have to use the ratio test. That's the difference between the two. Yep. So and then n going from 1 to infinity, negative 1 n over 5n. So this negative 1 n doesn't create any problem because since we take absolute value, it's going to go away. Okay, so the 5n says that this is the ratio test. Good. And the next one is, so let's try this. So let's say sigma n going from 2 to infinity, negative 1 n cube over 4 to the n. Yeah, this is a really good candidate for that. And then so how about this one, sigma n going from 1 to infinity, so let's say 3n n squared over factorial n. Okay, so this says that this is a ratio test. This says that this is a ratio test. Good. And then this one, sigma n going from 1 to infinity, n factorial over n to the n. Again, if it is upside down, you can use the direct comparison test for this, but here you cannot. And then so these problems, so sigma, let's say k equal 1 to infinity, k e negative k. Okay, so this one, and then we can have sigma n going from 1 to infinity, ln n over n to the n. Sigma n going from 1 to infinity, ln n over n factorial square. And then a little complicated one, let's say n going from 1 to infinity, negative 1 to n minus 1, 2 to the n minus 1, e to the n divided by 3 to the n plus 2, n factorial square root. Okay, so it can be complicated like that, but you can simplify all of them very nicely. So these are all like ratio problem. Good, ratio test. And then I'm going to give you cases where this test gonna fail. For example, these three. So if you try to use the ratio test for these, it's not gonna work. So n going from 1 to infinity n over ln n doesn't work for this. Sigma n going from 1 to infinity. Okay, actually here you cannot have n equal 1, it will be n equal 2 because ln is in the denominator. And then for this one, 1 over n doesn't work. Sigma n going from 1 to infinity 1 over n squared up. Any powers like that, if you have just the p series, it's not going to work. So in general, it doesn't work for the p series. So if you have n equal 1 to infinity, 1 you have n to the p, it's not going to work. So that's something we cannot use the ratio test. And then also if you try to use for this one, sigma n going from 2 to infinity 1 over n ln n. Okay, for all of these the ratio test fail. Ratio test fail for this problem. That means don't try for these problems. The ratio test is not going to work. Good. For example, the last one, you can use the integral test to do the last one. So that's why sometimes there are some ratio test is one of the very powerful tests, but unfortunately there are certain series that doesn't work. Good. Yeah, and then yeah, so that's about that. And then so let's go to the root test. Okay, root test is very similar to the ratio test, but there are major applications of that. So the root test so used for series with an nth term is of the form you have some kind of function, not a constant, to some n power. So this n is the one, and here you also have a function, not a constant. You have some kind of function. Then you try to use the root test. So that's kind of indicator. So what's the test? So root test. So the root test is again row. Now what we can do, you take the nth root of the nth term. So we can take the absolute value of the nth term and find the nth root of the nth term. Again, the same criteria as the root test, ratio test. So if it is less than 1, this number is less than 1, it's going to converge. Actually, it's absolutely converge. We know the absolute convergence implies convergence. And if it is greater than 1, diverge. And if it is equal to 1, test fail or inconclusive. Inconclusive. So you have to use other tests. Okay, so use other tests. Very good. And then there are a few things that you need to remember when you try to use a root test. For example, limit when n goes to infinity 1 plus x over n to the nth power, which is simply e to the x for any x. Okay, any x. So this is one major result that we use sometimes. So it's simply ax. So it's be 1 plus x. X can be positive or negative, it doesn't matter. Whatever the x value, you get e to the x. That's one thing. And also some other special limits. For example, limit when n goes to infinity, let's say n root of n, which is 1. Nth root of n, that means the cube root of 3. 10th root of 10 is all 1. And the other one is the limit n goes to infinity a to the nth root, which is always 1 for any positive a. So here we assume that A is positive. And then if A is between 0 and 1, we know that uh, the limit of an is 0. We know that the limit of an is 0 because when you increase the power of n, what's going to happen since a is in between 0 and 1, it's going to get smaller and smaller and smaller, so it's go to 0. Good, so that's about that. And these are the problems that you can try using the ratio test. You can try these problems. So let's exercise. So these are the typical examples. So let's say sigma n going from 1 to infinity to n plus 3 over 5n plus, yeah, it doesn't really matter, plus 4, something like that, to the nth power. This n tells you that it is the, because you see a function, you see it's a function to nth power. This is a root test, and you can see that once you take the root and take the limit, you're gonna get 2/5, which is not equal to 1, which is less than 1, so this has to converge. And as the next one, you can try sigma n going from 1 to infinity. This one, n minus 3 over n to the n squared. Yeah, to the n squared. You can see this term tells you that you have to use a root test. And then the next one, n going from 1 to infinity, n over n plus 1 to the nth one. And you can see that when you try to use the root test, you see the test fail. But this problem we consider as the test under divergence test. Okay, the first one. So you can, even though you cannot use the root test, you can still use the divergence test. Good. And some other ones. You can say sigma n going from 1 to infinity. Tan inverse n to the nth power. Tan inverse n to the nth power. We know the tan inverse n goes to, when n goes to infinity, it's going to go to pi over 2, which is a number. It's going to go to pi over 2. Good. And then sigma n going from 1 to infinity, negative 2 to the nth power over n to the n. This clearly, these n's tells you that you can try the root test. And the next one, n going from 1 to infinity, negative 1 n minus 1 over ln n to the nth power. This nth power also tells you that this is the root test. And I'm going to give 3 more. So try to kind of identify what is the indicator. So it is the nth root minus 1 to the nth power. This n tells you that this is a root test. And 2 more from 1. 1 is just a number. So if you don't like 1, let's put some other number. Let's say 4 to infinity n to n divided by 1 plus n to the 3n. Again, this n tells you that this is the root test candidate. Good. And then as the last problem of this type, 1 to infinity n over n squared plus 1 to the nth power. This n tells you that this is a candidate for the root test. Good. So these are some of the problems, and you can see the familiarity. This is n here. Yep. Okay. Good. So let's do the last one. So this is the what we call the integral test. Integral test. So what's integral test? So you have a series. The nth term is a function where if you try to integrate this function, I just put 1 here, it can be 1 or 2 or any other number to infinity. If you try to integrate, so this one is easy to integrate. This idea is easy to evaluate. Okay, that's the idea. It's easy to evaluate. So if you try to look at this integral, it's very easy to evaluate. So if that is the case, if this is to evaluate, then what we can do, we're going to use the test. So what the test says, the first one, what the test says, that because this is improper integral, this improper integral converge. The test says that if the improper integral converge, the series converge, integral diverge, the series diverge. But there are few conditions of this function. This function has to be positive, continuous, and decreasing. So the function fx is positive, continuous, and decreasing. All the conditions are important. At least you need to mention that, because sometimes it's easy to see positive, continuous, and decreasing. And then what it says that whatever happened to the so converge if and only if the integral converge. When you say if and only if, it means that if it converge, it's going to converge. If it diverge, it's going to diverge. That's what it means. Okay, converge or converge, diverge. So if it diverge, then this is going to diverge. Okay, the same thing happen. That's why if and only if means whatever happened to the integral, the same thing happened to the series. Okay, so these are some of the candidates for that. So you can see these are easy to integrate. The corresponding series, corresponding integral is easy. So sigma n going from 1 to infinity, n e minus n squared. This is just a u sub problem. And then n going from 2 to infinity, 1 over n ln n. So we could not do this problem earlier. So we know that we try to use the ratio test, doesn't work, root test doesn't work, all those other tests doesn't work, but this is very easy to integrate, so that's a good candidate for that. And then sigma n equal 3 to infinity, 1 over n ln n square root. Yeah, that's also a good candidate for the integral test because it's very easy to integrate. And then you can see this one, sigma n going from 1 to infinity, tan inverse n over 1 plus n square. This is also a very nice integral. You had to use up. And then how about this? N going from 1 to infinity, e to the 1 over n squared. Good. Yeah, and then also let's put like some obvious one, like Sn going from 2 to infinity, 3 over n minus 1 square root. Like you can use the integral test for this one, but if you try to use the what we call the limit comparison test, much easier. So this problem you can do using a limit comparison, direct comparison, and then also the integral test. Okay, you can try the direct comparison test works, and the limit comparison test works, and then the integral test also works. Integral tests. Okay, so all three works for this one, and if you try to use the ratio test, it doesn't work for this problem. Good. Um, so this is yeah. So these are all the different tests. Now what I'm going to do as the last thing, let's pick some random like different examples and see what tests we can use. I'm not going to do the whole problem, but I will tell you what test to use. So let's just do like some practice problems. Okay, few practice problems. So let's say practice problems. So please try this one after you try to understand all those different types. Then that way it's easy. Then you know what's going on here. So let's start with this one. So let's say n going from 1 to infinity, n minus 1 over, I'm just pick some numbers, 2n plus 3, something like that. So if you look at this one, and you can see this is a rational function, that's the first thing. And I try to find the limit of this n term. Okay, that's the first thing, and you can just do a mental calculation, and you can see that in this case n is simply n minus 1 over 2n plus 3, and we have two polynomials, top and bottom, have the same degree. That means you only need to worry about the largest terms. They have the exact same degree. That means this is simply going to converge to the ratio. That means 1/2 as n goes to infinity, which is not equal to 0. Okay, so since this is not equal to 0, this has to diverge by the test for divergence. So we can use test for divergence. Test for divergence. So you can see that's how we figure out. You try to look at the limit of the term, so and then you can see what's exactly going to happen. So from that you can see this is not a, this is just diverge. Okay, so you don't want to waste using other tests. Good. And then, so how about this one? And then try this as an exercise. So let's say sigma n going from 2 to infinity, tan inside you can say pi n squared minus 1 over say 3n squared plus 4n plus 10. Okay, something like that. So try it. Once you can see that this one also gonna diverge. Okay, so look at the next example. So number 2, so let's say sigma n going from 1 to infinity, n cube plus 1 square root divided by 4n cube minus 4n squared plus 2. So if you get a like algebraic expression, you can see this is just an algebraic expression, the whole thing. When you have algebraic expressions, it tells you that you have to use the limit comparison test. So now the question is what we're going to compare with, because when you want a limit comparison, you have to look at, you need the comparison test. So what are you going to do? N equal 1 to infinity bn, we can call that as bn. So where, what is bn? So you can see bn is how to get, you look at only the largest terms. So if you look at the largest term, it is n3 square root. In the bottom it is 4n cube. You can always do that. You only need the largest term. The reason is n goes to infinity. We look at the limit. That's why we can do it. And now we can simplify. This is n to the 3 over 2, and here we have 4n cube. Now you can simplify. This n3 has the 1.5. That means this can simplify to 1 over 4n 1.5. The reason is The top is simply 1.5, so this is equal to 1.5, and bottom we have 3, so it subtracts, so we get 1.5. Now this is just a p series with p equal p greater than 1. Okay, so you can see this is a p series. So here p equal 1.5, which is greater than 1, implies the p series converge. This means sigma 1 over 4 n to the 1.5 converge. Okay, so we know that by the p series test. Okay, now what we can do, we can look at the limit comparison. So after that we can use the limit comparison test. Use the limit comparison test. Good. And then you can see that it has to converge because this one converge. Number 3. So let's say we have this one, sigma n going from 1 to infinity n squared e to the negative n cube. So what you can do here is you can see that this is very easy to integrate. This is just a u sub problem. So we can say since the corresponding integral 1 to infinity x squared e to the negative x cube dx is easy to integrate. This is easy to evaluate. This is integral, easy to evaluate. Use the integral test. Use the integral test. And this problem you can also do using just the basic like a direct comparison test. See how to use the direct comparison test for a problem like that. Okay, so can be used the direct comparison test as well. Direct comparison test. The reason is we know that the ex is simply 1 plus x squared over factorial 2. Is something we learned before. x3 factorial 3, like that. Okay, so we can do that. So that's the fact. So see whether you can use a direct comparison test to do this problem, but basically this is a integral test problem because it's very easy to integrate. The corresponding function is easy to integrate using the u sub. You're gonna pick this p gonna pick as u. Then you can see the derivatives right there. Okay, just about that. And then next problem, number 4. So number 4, this one, sigma n going from 1 to infinity, negative 1 to the n squared divided by n to the 4th power plus 3. So so this is n. Now you can see that this is an alternating series. So since this is an alternating series, because you can see the terms change the sign, so we can say a series is alternating. Series is alternating. Series is alternating, and the limit n goes to infinity, an equals 0. So this is equal to 0. So we cannot use the test for divergence. So you have to use the alternating series test. Okay. So we can use the alternating series test. This problem also can be done using the absolute convergence test. What's absolute convergence test? Instead of the original series, we're going to consider the absolute series. Okay. So also, you can say also the absolute convergence test works. So absolute convergence test. Absolute absolute convergence test works. Okay, you consider absolute series, and then you can because you can say if you look at absolute series that you can compare with 1 over n squared, that's a p series p equal 2, so it can converge. So the absolute series converge. Since absolute series converge, the original series converge. So these kind of ones are what we normally call the conditionally converge. Actually, this one is absolutely converge. So absolutely converge, so the original series converge. But there are some series they do not converge absolutely. Okay, good. That we can discuss in another one. Number 5. Let's say sigma n going from 2 to infinity. You can say n over ln. So how to do these problems? N over ln n. So if you look at this problem, so you cannot use the ratio test because if you have ln n, we are not going to try the ratio test for that. So but you notice something, so we can see, I'm going to say since, because ln n is always smaller than n because of the shape of the graphs. You can see the two graphs. The natural log graph go like that. This the y equal x. This is ln x. So that means it's always smaller than x. So because of that, so you can say since ln n is smaller than n, this says that n over ln n is bigger than 1. Right? So we can simply use the direct comparison test. So use the direct comparison test with the series. The comparison test is simply 1. Just pick 1 because that one diverge, and so this has to diverge. Okay, so use the direct comparison test. Good. The comparison test is just 1, and then let's do 2 more. So the next one is number 6. Sigma n going from 1 to infinity 2 to the k over factorial k. The factorial implies that this is a ratio test. Okay, factorial k implies that ratio test is used. Good. And number 7, let's say sigma n going from 1 to infinity n minus 3 over n to the n squared. So the n squared term, that means a power function of n, implies that, so you can say some function to this term implies that the root test can be used. It's a root test problem. It's a root test. Good. And as the last one, so let's say sigma 1 over 3 plus 2 to the n, something like that, n going from 1 to infinity. So what can we do? So you can see that 3 is just a constant. So what is the dominating term is 2n. That means so it looks like 1 over 2n. So that means 1 over 2n means is geometric series. So you can use the geometric series. You compare with the geometric series. So you can see this is close to, this is close. close to 1 over 2n. All right, this is just a geometric series. Uh, so use the and then what we do after we get that, then you can use the limit comparison or direct comparison. Okay, so use limit comparison test or the direct comparison test with the geometric series. Okay, because the geometric series that's going to converge, now we use the limit comparison test, and you can see it's because same limit, so that means this has to converge. So this is the way we can try some of those tests, and you can see it's not just a wild guess. Depending on the terms, you can see that what test has to be used. I hope this will help you to learn this properly. Thank you. And you can also see another video which has all series tests in one video that has nice examples, like completely solved problems in there. So you can look at that along with this, so that you can get the complete understanding about the technique. Okay, so there will be a link in the description which says that the all-in-one series tests. Okay, so make sure that you're going to look at that. That's going to help you to understand how to use them step by step. Okay, thank you.